Yay!
Yay! Hey, what's up? It's time for another Projectiles problem. This one is going to be a little bit more general because it's going to be a launch. So last time we did one where the initial motion was just horizontal, but now the initial motion is going to be vertical as well. So we're just going to launch something off the ground. Maybe we're kicking a ball or hitting a golf ball or whatever, hitting a baseball close to the ground. Anyway, the thing that we're doing is launching something with an initial y velocity. Before, it was just horizontal. All right, so typically the thing that we're going to be trying to find is that r, the range. That's called the range, which is delta x, right? How far does it go before it lands? That's what we're interested in. How do we do it? Well, what we're going to need to do, remember the idea is we start with these two equations that we had last time. And we separate the motion into x motion and y motion. But notice, I mean, that initial velocity, it's going to have some number like, 30 meters per second, or what did I say? In this case, let's do 40 meters per second. And it's going to be at some angle, right? So it's mixing up the x and the y's. So what do? We go back to our vectors and we separate this into x components and y components, because that'll give us x motion and y motion. All right, so our x motion, our x motion is going to look something like this. It's going to be along this direction. And our y motion, for some reason, I've changed y to be green, but whatever. So that's going to be our VIY, and then this is going to be our VIX. All right, so we just need to separate that into components, but we know how to do that. VIX is going to be VI cosine theta. In this case, it's just going to be 30 degrees. Why don't I write down the 30 degrees? And 40 cosine 30 is going to be like about 35. So out of that 40 meters per second, 35 meters per second is in the x direction. About, I think it's like 34.6, but I'm just going to round up to whole numbers just to make things a little bit easier. VIY is VI sine 30. Sine 30, you should put that in your head, because that's going to be an angle we'll use over and over and over again. And sine of 30 is just a half. So 40 times a half, so it's 20. Its vertical speed is 20 meters per second. Neat. So I've got VIX and VIY now. So it looks like I can start looking at my equations and figuring out what the range is. Okay, now what I need, so I've got, look, range is VIX times t, right? I've got VIX. We're done, 35 meters per second. But I don't know this. I need to figure out this. I need to figure out how long it's in the air. Remember, that was almost always we're going to want to know that. That's going to be our key to figuring these things out. So how do I figure out how long it's going to be in the air? What I can do is go to the y equation. Again, that's something we're going to do pretty often. That's how we figure out the time. So from the y equation, along its path, what is the change of y from beginning to end? Because what I want to know is how long it's in the air from beginning to end, right? Well, what is the difference in the y coordinate from the beginning to the end? Okay, so here, let me say it like this. Here we launch and land on the ground at the same point. Next time, we'll do the more general case of landing maybe up on a cliff, or launching from up on a cliff or something. So this is going to be the slightly simplified case of launching from the ground and landing on the ground. And we'll see how it differs later. Okay, so if I launch from the ground and then land on the ground, what's my y final minus y initial? They're both 0, right? I'll just call y equals 0 to be the ground. So I've got this. So I've got 0 equals VIYT. Well, I've already got, it's 20, right? I've already figured out what that is. 20 times t minus 1/2 gt squared. Just to keep things simple, we're going to approximate g is 10, right? So 1/2 of 10, 5. So this is just going to be 5t squared. Well, that's not too bad. So 5t squared is 20t. I can divide out one of the t's because I know that one of the times when it's on the ground is when I launch, but I want time other than 0. So I'm going to cancel out one of those t's, and what you're going to get is that t is 4 seconds. All right. Cool. So I'm kind of done, right? I can figure it out. Now that means that the range, how far does this thing go? If it's launched at 40 meters per second at 30-degree angle, what's the range? It's VIX times t. Well, now I know what t is. So this is going to be 35 times 4. What is that? That's like 140. Like 140 meters. All right, cool. So now I know the range. Okay, so that problem is solved. Let's do it in general. Let's solve every one of these problems, right? Let's get a general formula. Generally, the range, that's our delta x. It's VIX times t. All right, so that's going to be VI. In other words, if I'm just given a speed and a launch angle, I should be able to figure out the range. Like in one step. Let's just get a formula that'll tell us the whole thing. Times t. Okay, generally, how am I going to figure out what t is? And 0 is going to be vi sine theta times t minus 1/2 gt squared. All right, so dividing out one of the t's, that's going to mean that 1/2 gt is equal to vi sine theta. So solving for t is 2 vi sine theta divided by g. That's the total time this thing is in the air. Let's box that because that'll be a useful thing to know. There's the total time this thing is in the air. Well, then I can plug that back in to find r in general, right? So this means that r, well, let me get myself, sorry, I'm sort of working backwards on the screen just to give myself more room. So r is going to be vi cosine theta times this t we just found, 2 vi sine theta over g. We can write that a little bit more simply. So this is going to be vi squared 2, let me write it suggestively, 2 sine theta cosine theta over g. And then you're leaping out of your chairs, right? Because if you've had trigonometry, maybe you recognize 2 sine theta cosine theta. What the heck is that? That's the same thing as, I'll just write it one more slightly different way, vi squared 2 sine theta cosine theta is sine 2 theta. You might remember that. Maybe you don't. Over g. And there we go. So now we know, oops. Let me box that. Now we know if you're given a VI, an initial speed, and an angle, you just plug those in and you can get the range. We don't even have to do that much calculating. This is just a little bit easier because it's one trig function to stick in the calculator instead of 2. But it doesn't really matter. So plugging in the VI and the sine 2 theta, you should verify again that you get about 140 meters for the range. That's it. That's like every launch problem where you launch from the ground and land on the ground. We know our time it's in the air, and we know our range. We could, if you want, we could figure out the maximum height, right? me figure out the maximum height over here real quick. Why don't we use another one of our kinematic formulas to do it? If I want to figure out the maximum height, I could go v final squared equals v initial. This is in the y, right? Squared plus, well, let's go ahead and put this in there. It's plus 2a delta x from last chapter, but remember our a is minus g, so this will be minus 2g, and this will be our delta y. This is going to be our height, the displacement. There we go. And then one thing to realize, what happens when something gets to its maximum height? That means it's kind of turning around. It's momentarily stopped, right? So our final y velocity at that point is going to be 0 at maximum height. So our maximum height is just going to be what? V initial sine theta squared over 2g. And if you work this out, if you plug these numbers in, you should get about 20 meters. There we go. So now we know the maximum height that this thing goes. We know the time that it's in the air. What's the time to maximum height? That's kind of a cool thing. T sub h. Let me make sure that's a T sub h. The time to get to maximum height, well, it's a totally symmetric trip up and down. So if I know how long it's in the air, just divide it in half, and that's how long it takes to get up to maximum height. And so that's just vi sine theta over g, right? Okay, so we know a lot of things about the path of this thing. If I know an initial speed and a launch angle, I can calculate the range, I can calculate maximum height, I can calculate the time in the air, the time to maximum height, and so on. So we've just sort of completely solved the problem. Let's go just a little bit farther. What if I do this? What if I then say, I'm going to put a wall. Maybe it's like an outfield wall in baseball. I'm going to put a wall out there. Let me go to the next. Let me go to a clean page, right? Okay, so here's the situation. I've got a path. There's my VI. And then somewhere out here, I've got a wall. And let's say that this wall is 15 meters high. What I want to know is the ball going to clear the wall, the one that we launched before? So before we said VI equals 40 meters per second. The angle is 30 degrees. Does the ball clear the wall? Now, let's put this wall, it's a good sort of outfield distance. Let's put the wall 120 meters out. All right. Is the ball going to go over the wall? Well, okay. What you know is that the range of this thing is 140. So you might think, well, sure, it's going to go 140 meters. The wall's only at 120. What we don't know is the ball going to bang into the wall before it comes down, right? Does it clear the wall? That's what we're trying to find out. So if I'm going to do this, there's two ways that I can go about it. Okay, here's method A, and maybe you've thought of these already. One thing I could do is to figure out how much time, and I'll write these out so that the reasoning maybe is clear. How much time for the ball to go 120 meters? Well, let's figure that out. The amount of time it takes for the ball to go that distance is just going to be delta x over v I x. That's just going to be 120 meters over, what did we say? In the x direction, it's going 35 meters per second, right? And so we get, what did I get? 3.4 seconds. Okay, so after 3.4 seconds, it's gone 120 meters. But what I want to know is, at that point, what is its height? So the second part of this is, what is its height at this time. Well, this isn't so bad. All I have to do is just use the equation that tells me the height at any time. That's this one. The height at any time is just VIY times t minus 1/2 gt squared. Okay, so let's see. At 3.4 seconds, how high is this thing? It's going to be, our VIY was 20 in the y direction, times 3.4 minus half a g is 5, times 3.4 squared, and what did I get? I got 10.2. Nope. So it will not clear the wall, right? At this time, it's gone 120 meters for sure, and it's not on the ground yet, but it's coming down. It's only at 10.2 meters high, so bang, it's going to hit the wall. Neat. There's another way that you could do it, though, and this is going to kind of lead us into where we're going next time. Here's another way you could do it. The other way you could do it is you could take that equation we just used, the height at any particular time, turn that around and say, at what time is it 15 meters high? Now, we already figured out the maximum height was 20, right? If the maximum height was like 10, well, then we're done. We know it's never going to get above the wall, so we don't have to worry about it. But we know that it gets up to 20 meters high. So let's figure out at what time is it 15 meters high? And then where is it on the x-axis at that point? All right, so what I can do now is I can just put in 15 for delta y, right? The final position is going to be above the initial position by 15 meters. So this is going to be 15 is going to be, again, 20 times t. I'm trying to find the time, minus 5t squared. I'm trying to solve for time, right? So initially this looks a little bit tougher to do because I got to solve for t. How do I solve for t? That's a quadratic. It's a quadratic equation. So but that's okay. You've probably done quadratic equations before. Not a big deal. Okay, let's get it in standard form. I could subtract 15 over, right? But here's my advice from many times making this mistake. Whatever's in front of the t squared, get that to be positive. In the quadratic formula, that's our a, right? So my advice is always make a positive. Make that thing positive. So bring the t squared to the other side. Make this positive. 5t squared minus 20t plus 15 equals 0. I'll show you why in just a second. But my advice is do it this way. Always make that t squared coefficient positive whenever you can. Well, first of all, to make it pretty easy, I just divide out the 5. Let's factor out a 5. So t squared minus 4t plus 3 equals 0. What can I do now? Well, one thing you could do is just remember the quadratic formula. So t is, some people learn it like a song, right? I don't know. So anyway, it's minus b, so that's going to be 4 plus or minus the square root of b squared, 16 minus 4ac, that's 12, over 2a, that's 2. So if I do that, I'm going to get 4 plus the square root of 2, square root of 4 plus 2. So I'm going to get 3 seconds, 2 answers. I'm going to get 3 seconds and 1 second. And if you think about it, that kind of makes sense. At what time is it 15 meters high? I guess I didn't draw this very well because I put this above the maximum height. Where is it 15 meters high? Well, it does it twice, right? It does it on the way up, maybe right here, and then it does it on the way down over there. So getting 2 times makes perfect sense. We're going to be interested in the 3 second one because that one is going to be closer to the wall. That's when it's coming back down again. Okay, so now figure out when it's 15 meters high, how far away from the launch point is it? So delta x is just going to be Vx 35, we said, times this 3, 105 meters, right? So again, it's at the top of the wall. It's the height of the top of the wall, but it's only gone 105 meters and it's coming down. So no way is it going to go another, 15 meters and then clear the wall, right? It's going to be coming down. So both of these methods are going to lead you to getting the right answer. So it's not at the wall yet, is what this one's telling you. By the way, you don't have to use the quadratic formula. Maybe some of you spotted this. T squared minus 4t plus 3. We could have done, let me just make this little aside. You could have seen that that's pretty easily factorable, right? This is the same thing as t minus 3 and t minus 1. Oops. Equals 0. Because if you multiply that back out, you get the t squared minus 4t plus 3. And that has solutions t equals 3 and t equals 1. So you could, if you're good at factoring, keep an eye out for things that are easily factorable. But generally, you're going to have to use the quadratic formula. Okay, I wanted to show you this because this second thing, figuring out at what time is it 15 meters high and solving the quadratic equation, that is where we're headed next time. That is how we're going to address the more general case of launching something off of a different height than where it lands. So that's sort of the spoiler alert for next time.